Drum brakes have a drum attached to the wheel hub, and braking occurs by means of brake shoes expanding against the inside of the drum. With disc brakes, a disc attached to the wheel hub is clamped between two brake pads. On light vehicles, both of these systems are hydraulically operated. The brake pedal operates a master cylinder. Hydraulic lines and hoses connect the master cylinder to brake cylinders at the wheels. Most modern light vehicles have either disc brakes on the front wheels and drum brakes on the rear, or disc brakes on all four wheels. Disc brakes require greater forces to operate them. A brake booster assists the driver by increasing the force applied to the master cylinder when the brake is operated. A power booster or power brake unit uses a vacuum to multiply the driver's pedal effort and apply that to the master cylinder. This increases the pressures available from the master cylinder. Units on gasoline engines use the vacuum produced in the intake manifold. Vehicles with diesel engines cannot use manifold vacuum, so they are fitted with an engine-driven vacuum pump. The most common booster operates between the brake and master cylinder. It increases the force that acts on the master cylinder. Whenever the brake pedal is depressed, a pushrod opens the vacuum control valve. The level of assistance this power boost gives depends on the pressure applied to the brake pedal. The anti-lock braking system prevents wheel lock or skidding, no matter how hard brakes are applied or how slippery the road surface. Steering stays under control and stopping distances are generally reduced. It consists of a brake pedal, a master cylinder, wheel speed sensors, the electronic control unit or ECU, and the hydraulic control unit, also called a hydraulic modulator. The ABS control module, or ECU, sends commands in the form of electrical signals to the hydraulic control unit. This unit executes the commands using three solenoid valves connected in series with the master cylinder and the brake circuits. One valve for each front wheel hydraulic circuit, and one for both of the rear wheels. In normal non-ABS braking, brake pedal force is transmitted to the master cylinder, then through the solenoid valve to the brake unit at the wheel. When the signals from the wheel speed sensor show no tendency for the wheel to lock up, the ECU does not send any control current to the solenoid coil. The solenoid valve is not energized, and the hydraulic pressure from the master cylinder is supplied to the brake unit at the wheel. When the control unit detects any lock-up tendency, perhaps from too rapid wheel deceleration, it sends a command current to the solenoid coil. This causes the armature and valve to move upward and isolate the brake circuit from the master cylinder. That keeps the pressure between the solenoid and the brake circuit constant, regardless of whether or not the master cylinder hydraulic pressure rises. If the sensors signal continuing excessive wheel deceleration, the control module sends a larger current to the solenoid valve. This lowers the braking pressure by moving the armature up further, opening a passage from the brake circuit to an accumulator, a temporary reservoir for any brake fluid that flows out of the wheel brake cylinders because of the fall in pressure. A return pump sends this brake fluid back to the master cylinder. If the sensors then signal that the lower pressure has allowed the wheel to speed up, the ECU stops all command current, which de-energizes the solenoid valve. The pressure rises, and the wheel is again slowed down. Whatever the phase of operation, pressure in the circuit can never rise above master cylinder pressure. Modern cars use tandem master cylinders to suit divided or dual-line braking systems. A divided system is safer in the event of partial failure. Fluid loss in one half of the system still leaves the other half able to stop the vehicle, although with an increase in stopping distance. A wheel's braking ability depends on the load it's carrying during braking, so the type of vehicle is a major factor in how its system should be divided. A front-engined, rear-wheel drive car has around 40% of its load on its rear wheels, so its braking system can be divided in a vertical or front-rear split. This puts the front wheels in a different system from the rear wheels. If one half of the system fails, the front or the back, there's still enough separate braking capability left in the other half to stop the vehicle. This doesn't work well for a front-wheel drive vehicle. A load of about 20% on the rear wheels can't provide enough braking force to stop the vehicle. Front-engined, front-wheel drive vehicles use a braking system split in a diagonal, or X. The left-hand front brake unit is connected to the right-hand rear unit, and the left-hand rear to the right-hand front. If one system fails, a 50% braking capability is left in the other system. Dual proportioning valves maintain optimum braking in each system. A system that partially failed would cause severe braking pull on a vehicle's suspension, so suspension geometry is usually revised to counter this. An alternative arrangement for front-engined, rear-wheel drive vehicles is an L-split. The front disc brake units have 4 piston calipers. 2 of the pistons on each front unit connect to the right-hand rear, and the other 2 pistons of each unit connect to the left-hand rear. As with the X-split, if there is a failure of either half of the system, it still leaves 50% braking capability.